Flappy Bird Jellyfish Edition. And this is what you're going to be making today. If this is your first time with Swift, or your first time with Xcode, let me be the first to welcome you to the Swift and Xcode world. And this video is really for people who want to get their hands dirty and being creative. This is for people who want to make the jump from GameMaker, from Godot, from Flash, and want to make something with a real full-fledged object-oriented technology and make a full-on iOS game. So in this video I'm going to go very slow explaining every little thing about Swift and X and SpriteKit, because this is for the beginners. So if you have little experience with programming, this is for you, because I'm going to explain every little thing. First project in Xcode. Click on Create New Project. From these options you can select templates for getting started with your new project. A single view application does not use SpriteKit, and this game template uses SpriteKit. Select that one. Let's name it Flappy Fish. Language is Swift. Choose SpriteKit for this technology, and we're not using Gameplay Kit. Create a Git repository. Tour of Xcode. If you click this little blue file up here, this is the project folder, project file. It'll show you all the attributes of your project. You have your identity, your code signing, and this is where you can select your team, your development team. If you haven't made a development team yet, you can do that with your profile, your development profile. Or you can select none if you haven't done that yet. Select your deployment target, universal devices. Here you can set the orientations allowed by your game. This game is going to be in portrait mode only, or holding the phone upright. So if you deselect landscape, it will not rotate. The game will not rotate if the player rotates the phone. The status bar of your phone is the stuff in the top that tells you the time and the battery. You can hide it or not hide it. And there's a lot of stuff in here that you'll discover over the many months of being a developer. Now in the root folder, named after the project, we have the app delegate. Now I can say I hardly ever go in here, but you might find it useful one day. These files are these files of .sks type are your scene editor and your actions editor. In your scene editor you can visually put assets into your scene. So this label you can drag around and you don't have to, it'll appear and you don't have to use a lick of code. Now if you look up here in the top right, you can toggle the utilities bar. Now the utilities bar on the bottom will show you options of objects you can put into your scene. You can put in a color sprite. This structure right here shows you how your properties are structured, and the order does matter. The ones on the bottom are drawn last, so they will be in front of the ones before them, unless you change the Z position here. So if you select an object, it'll show you its properties in this navigator window right here. You can give it a name, which is important for referencing it in code. You can give it a texture, and if you import pictures into your assets, you can do that. Different types of objects will have different types of things you can change about them. With a label you can change the font and the text and all that stuff. There are many objects here you can explore. The actions SKS file I'm not quite as familiar with, but actions are what make objects move around and do visual things. And here's the code for the game scene. Each of these Swift files generally hold a single class. So at the beginning of this file we declare a class called GameScene, and all the stuff in this file will be contained within this class. Now to help you see larger pieces of code, you can fold in brackets by going Option Command left arrow, and you can expand it again, Option Command right arrow. You can close in smaller, more nested brackets by putting the cursor inside the brackets and going Option Command left. So I just folded this function And I can do that for even more smaller things like this let statement. And if I wanted to expand everything, I can go Shift, Option, Command, Right. Our view controller is the main view that is handling our scene. So without this view controller, we wouldn't have a scene. Inside this view controller, our scene is being created as an instance of the scene, and then the view is presenting that scene onto itself. Now usually in apps that do not use SpriteKit, we use the main storyboard. Here's the main storyboard. Now in an app that does not use SpriteKit, you usually have here is the same concept as our scene editor, except there's different objects. So you can drag in some different view controllers. So yeah, I just dragged in a view controller, and then you can make the app switch back and forth between these two view controllers and do whatever you want with those. Okay, we'll get rid of this and go back to our game scene. Mostly the entire game will be handled within our game scene. Now, to use images in your app, you just drag them into your assets.xcassettes folder. And here are some images I'm going to use now for our Flappy game. Images drawn courtesy of Nathan Richard. I'm going to highlight them all and just drag them into our Xcassettes, and then there they are. Now the code that it generates for our game scene, we can go ahead and get rid of everything and just do a fresh slate, because we're starting our game from scratch. Okay, now this is called a code snippet. I'm going to start typing something and then hit enter to complete the code that I wanted to use. This is something that I made as one of my custom code blocks. And code blocks are very, very useful, especially in helping your workflow get so much faster. So here's how you make your custom code snippets. Down here, you can look at your menu of code snippet in your code snippet library. Any of these that say user are ones that I made, and there are many others that just come with Xcode. They're kind of useful, I guess. Now once you're done copying all this down, because this is a blank slate game scene that I use a lot, what you're going to do is highlight it, click down for a couple seconds until you see the pointer arrow. Now drag it over to the library when you see a green plus sign, let go. And here you can name your new snippet. My new snippet. I named this one game scene template, but you can name it whatever. And here's a completion shortcut for when you just want to type in a few letters and then have it appear. So you can say banana. Alright, so as soon as I start typing banana and hit enter, now it just appears. Great. If you want to get rid of this, you can select it and just hit delete. So whenever I say stop, write this down for a snippet, please do that. Okay, when you import a library, it looks just like this. Import SpriteKit. That is going to allow us to use all of the classes starting with SK. SK stands for SpriteKit. SK Scene, SK View. Without this, we wouldn't be able to use any of that. So if you comment it out, oh, how do you comment things out? Highlight and then press command/. See, now it does not recognize this class. A class in Swift, just like many other languages, is just something to hold properties. It holds properties and functions which execute code that kind of mess with those properties, and maybe other things. So all of the methods and properties of SK Scene I can access with game scene. That's what the override means. I'm using a function that already exists in its superclass. That brings us to functions. Whenever you see func, that's called a function. And what that does is it gets called. When it's called, it executes all the code inside of it all at once. Well, not really all at once. It goes one by one. It does go in order, but it happens so fast, you just can't see it. So a function has a name, which we're declaring here as didMove to didMove, and it has parameters. So here's our first parameter, view, and then this is the type that the parameter is. It's of type skView. So whenever this is called, it's going to receive a view. The basic functions of our game, of most games, have did move, which is this is going to be when the game starts. You have these touching functions, so this is going to recognize a touch. So just like the name suggests, this function is called when touch begins. This function is called every frame that touch moved. So when your finger moves, this is called every frame, and here we can, with this word location, we can tell where the finger is, what's the location of the finger. And this is called when the touch ends. This update function is what's called every frame, just like the comment says. There's another function used for when you want to call every frame, and that is did simulate physics. And if you just type that much and press enter, it'll show up. The difference between these two is mostly when you want to handle things involving physics in here. There are definitely many other functions that GameScene takes from SKScene, or I would call them the standard factory built-in functions, but we'll discover them in time. How does it work with getting the location of your finger? Well, in touches begin, we have a for statement, which means we are looping through an array. So anytime you see for, that means that is a loop. This function receives touches as a parameter. So there could be multiple touches, and all of the touches will be contained within this array of touches. So here we're looping through the array touches using this local variable t to represent each touch with each loop, or each iteration of the loop. Here we're declaring a new variable called location, and we're assigning it to the value of t.location in self. So how do we know what this location evaluates to? You can always test for a variable by typing print and then put the variable inside the parameters. Run the app, or build and then run the app by clicking on this triangle here, or you can press Command R. So if you run this and then touch all around the screen, you can see it printing off the location, the XY location of your finger. And you can tell that the middle is close to the 0, 0 point, and as you go up and to the right, the X and Y start increasing, kind of in the middle of this big coordinates. Now you can change where the 0, 0 point is, or the anchor point is on the screen. Come over here to your scene editor, and this origin point is given by this little crosshair right here. So go to the attributes and change anchor point to 0, 0. Now the crosshairs are in the bottom left corner, and that's where 0, 0 is, and you can tell by these numbers along the sides here. So we're actually going to get rid of these properties here. In our Flappy Fish game, the only label we really have is the score label. So here in the filter you can search for label, and then there it is, and you can just drag it in right there. There's our score label. Go ahead and name it score label, and you can set its text to be something to hold its place until we fill in a number. I'm going to go ahead and make the font bigger and bigger. Now let's go back to our GameScene.Swift, and now we're going to start like we usually do inside the function didMove to view. Instead of doing anything visual, we're just going to play around with Swift variables for a second. So a variable is declared either with let, so you can say let a equals 5, or with var, let b equals 7. What's the difference between these two? A let variable will never change. A will always be 5. A var will change, so b may change to a different value than 7. Now if you don't actually use the variables, it will give you this warning, because if you declare a variable but never use it, that's pretty much a waste of memory, right? But when you declare a variable, you can declare its type by going after the name. You can say colon and then the type. So you can do int, you can declare something as a CG float. There are many different types of data type. You can declare a character, a string. And means you can declare a bool. Bools are usually start with is awesome, and you can set it to true or false. So those are the basic types of data. But in Swift, since it is a Swift is strict with its types, so you'll learn how to deal with all the different types and be able to compare them. Now, in addition to variables holding these simple data types, they can also hold instances of objects. In other words, a class instance. Let's do that now. So now we're going to get visual. Let's make a sprite node. So you declare by giving it a name, let my amazing sprite, and then you assign it to a new sprite node like this. Now, if you have the open close parentheses, that's called initializing the variable. Now, you don't have to initialize it. You can say, instead of equals, you can say colon, and that'll just declare this variable as the type sk sprite node. Usually you would do an question mark, but we are going to initialize it. So go back to what we had before. Many classes give you options when you initialize. So if you do open parentheses and look at all the options, look what you have here. You can do a sprite node with a texture, which is just referencing an image. You can do a square sprite node with just a color and a size, or a rectangle. In general, what you do is you say image named, and then you reference the name of your image file in here. So let's make one of our jellyfish. So go to your X cassettes, and then you check out the name, and let's copy the name so it's exactly, and then you copy that into the string here. So we have our amazing jellyfish, but it's giving us a warning because we haven't done anything with it yet. We are going to say self.addChild my amazing sprite. So this means addChild is a function that SKScene has, and since GameScene inherits from SKScene, we can totally use this addChild thing. And self means that this is the GameScene's own function. It's the self, since we're inside the GameScene. If you want to refer to properties and methods of GameScene while you're in the GameScene, you don't have to use self, except sometimes you do in things called closures. So if you run it, you'll see our jellyfish appear. Look at that little jellyfish down here. He's appearing down here. And why is that? You guessed it, because his position defaults to 0, 0. And the position of the jellyfish is exactly in the middle of the jellyfish picture. So we always want to keep that in mind when we're positioning things. Okay, to reposition our sprite node, you can say my amazing sprite dot position equals. Okay, well, how do we know what to put in here? Okay, well, go back. Okay, so while you're typing position, well, if you press dot and look at the options, okay, the names on the right are the names of the properties, and on the left, this tells you the type. So we can do color, you can set the scale. Void means that it's a function that doesn't return anything. The little symbol way over to the left shows you whether it's a variable or a method, V or M. So a method will return something of type void or something. This is a variable, and this CG size here is telling you that it is a CG size texture. Okay, so what we want to do is position, wherever that is. Well, I can't find it, so I'm going to start to type in P-O. Oh, there it is, our first one. So what type is position? It is of type CG point. So whatever you set it equal to has to be equal to the type CG point. Now to make a new CG point, you can just type in CG point and then open parentheses, and this will give you options for making a new CG point. Pretty much you always go to this one, the XY, and you can position your jellyfish wherever. Let's see, 200 by 400. Look where he is now. Talk about scope. Real quick, we're gonna get rid of the utilities bar so we can really see everything here. Now I can change the properties of my amazing sprite in here within the did move, and that only after I declare it. But what if I wanted to do something with it when I touch the screen? So let's say in here, what if I wanted to say my amazing sprite and set its position to to the location that I touch at? the program's not going to recognize my amazing sprite in here. Uh-oh, how do we fix that? We have to declare my amazing sprite in the global scope. So, move it to up here. Now we're declaring it outside of any function. And usually you declare all your global variables first thing before any function. Now you can see that the variables you use from the global scope turn green. So these are your custom variables. And now you can access it, my amazing sprite, in touches begin. So right here after we get the location, we can totally set my amazing sprite.position equal to location. While I'm typing location, you can see that location is of type CG point. So this variable assignment is totally valid. Get rid of this. So wherever you touch, the jellyfish follows. That's pretty cool. Only reasons to really use SpriteKit is to exploit its physics engine, which can be kind of glitchy sometimes, so you have to be careful. Now to set gravity in your physics world, you say physics world. This is kind of a self.physicsworld.gravity. And what type is gravity? You can see that it's a CG vector. So you say equals, start typing CG vector, hit enter, open parentheses to see your options, and here you can initialize it with a dx dy. So that's the direction of gravity. Usually gravity is in a downward direction only, so we can say things are going to fall at a negative rate of -3. And I believe what that means is that so every frame, the downward velocity of everything will increase by -3. Now if you run it, well, will the jellyfish be affected by gravity? The jellyfish is not affected by the gravity, because we have to set that up. Okay, so this variable, my amazing sprite, is not very descriptive of what it is. I like things to be very clear. So we could change this to jellyfish, and we could change that everywhere. We could just copy and paste and paste. But undo all that. There's a much better way to do that. You can highlight the variable where it's declared and press Command-Control-E. And now we're editing all in scope. So we can change this, we can type this once and say jellyfish. And now everywhere where that variable was is now named what it's supposed to be named. Okay, we have to give the jellyfish a physics body. So jellyfish.physicsBody equals skPhysicsBody, and its initializing choices are, there's a lot. We can do circle, edge loop, polygon, rectangle, or you can have nothing, and that means its physics body takes no shape, but it still has a physics body, and it can move around and be affected by gravity. So now if you run it, you can see it's slowly falling. I'm going to click. So every time I click, his position reappears where I click, but he's still falling faster and faster. So now every time I click, so we'll start to head into the direction of Flappy Bird mechanics. So every time I click, I would like the jellyfish to jump up. So now instead of reassigning the position of jellyfish, so you can say PhysicsBody.velocity, and you can break that down even further into dx and dy. Now if you set it equal to a big number like 600, the jellyfish will suddenly have a upward velocity of 600. And that is pixels per second, not pixels per frame. So I'm clicking and he's jumping. It's kind of like on the moon though, gravity's so low. Now it's always good, if you have constants, like the 600 probably won't change throughout the game, it's always a good idea to make them global in scope. So you can say, you can call it let jump speed and colon make it of type CG float equals 600. So now down here in your touches begin, you can make 600 you can substitute in that variable jump speed So whenever you want to tweak that value, you can just look up at the top. You don't have to search. If you have hundreds of lines of code, you don't have to search all through this and try to find this 600 and change it. Best practices. Speaking of best practices, we're going to make Jellyfish into its own class because we're starting to get more and more properties of Jellyfish, and it really helps organize the code so we don't have so many things about Jellyfish inside our game scene. Command N for new file, Swift file, name it Jellyfish. And classes and their file names are usually capitalized. And here's a code snippet for you. A node with a sprites. So write that down for a code snippet. Very helpful. By the way, if you're importing SpriteKit, you don't need to import Foundation because SpriteKit contains Foundation, I believe. Okay, now we name our class Jellyfish. Jellyfish is going to be an SK node, which is really just a single point, but it's going to have a child of type SK Sprite. Yes, nodes have parents and children, and the root parent of everything is usually the game scene, which contains its children, which are shown on the screen, and the children can own children if you want to move things around together. We can put in our Jellyfish name here in our sprite. Now init. So the init function happens when it first gets created, and it's override because an SK node already has this init function and we are overriding it. Now we can pass in different things in here, and if we did that, we don't need the override keyword, but since we're not passing anything, we do need the override keyword. So when this Jellyfish first gets created, its sprite.size is going to be assigned to a CG size. So here you can give it an actual size. We can say 100 and height of 200, and the image will be stretched or scaled accordingly. Now here we can really get a true physics body of a certain shape. Okay, here's the deal with physics bodies. So a sprite is not a physics body on its own. It has to contain a physics body as a property, which is totally separate from the image. Now, the physics body usually takes the same shape as the image, or it tries to. And the more complicated your image is, and the more complicated your physics body is, the more processing your game is going to take. So simpler is better. So first, let's try making him into giving him a square physics body. So you can do rectangle of size, and here you can just pass in sprite.size. You already have that. And here are some properties of physics body. So is dynamic means whether or not it can move around and act under the forces of physics. Usually you set this to false if it's like some sort of ground or platform. Affected by gravity means is it affected by gravity. So this boolean tells if it is allowing rotation. Linear damping is kind of like air resistance. So how much is it slowing down as it goes through the air? Angular damping is like rotation resistance. How slowly is it slowing down its spin? So if you want to simulate space, you can set linear damping and angular damping to 0, so there's no resistance. Friction is when it's rubbing up against other surfaces, so this friction is the friction of itself. Restitution is its bounciness. So a value of 1 means extreme absolute bounciness, in which when it bounces off something, it doesn't slow down at all. Okay, these three properties have to do with collisions. We will deal with that in a little bit. So we made our Jellyfish class. You can think of classes as like a cookie cutter, because we haven't really actually made cookies yet. So back in our game scene, we're going to make what's called an instance of the class Jellyfish. So instead of our sprite node, we're going to say let Jellyfish equal, and then capital J for Jellyfish. And that's how you make an instance of our class. If you run it, it should do exactly the same thing as before, except now you're going to see the distorted image. So we can make the image back into a nice square of 100 by 100. Now let's make the coral reefs from the game. And remember, this is kind of like the pipes in Flappy Bird. So thinking about how the game works, we have two coral reefs that are going to move together. Now to me, the easiest way to do that is to make a parent node that is going to move. The coral reefs are going to be two children of that parent node, so that whenever the parent node moves, the two reefs move along with it, because a child's coordinate system is centered around its parent node. So first, let's make the coral reef. And then we'll make a separate class called Coral Reef System, and then that is going to contain the two reefs as children. Okay, so this is a code snippet of mine called, this is a subclass of SK_Sprite node, and we'll call it reef. So unlike the jellyfish, remember that was a subclass of SK node that had a child of a sprite node, but now the reef itself is a sprite node. Okay, so we initialize it, not passing in anything, and then its texture, we can declare it to be our reef picture. And just to make sure in our pictures or images, this is called reef, exactly what we want. So we're creating a texture and getting the image name reef, and now super init, so that's when it's actually being initialized. We pass in the texture in here, and then we can set a size here. And don't worry about the color, that doesn't really do much of anything. Okay, the reef size is going to be 300 by 800, because it's going to be kind of tall. Okay, its PhysicsBody is going to be initialized using its texture. And what that does is make a PhysicsBody that maps exactly the shape of the image. Now this is kind of expensive in terms of processing, but there's not going to be that many on the screen at once, so I think it's okay. So we pass in this texture into here as the texture, and then the same size. So you can go texture.size. The way it's going to move around is not with physics, but we're going to set its position every frame in the game scene. So therefore dynamic will be false. Mainly because when the jellyfish runs into the reef, we don't want the reef to be bouncing around as well. We only want the jellyfish to be bouncing around. So we have no gravity, no spin, so we don't even need any of these, because that has to do when it's moving around with physics. And then the collisions we'll deal with later. Okay, now make a new class, new file called reef system. And this is going to be an SK node subclass. Name it reef system. And we don't need this sprite property here. Okay, it's going to receive an initializer, so get rid of this override because we're going to pass something into this reef system. Call it gap space, because this will be the space between the two reefs, and it is of type CG float. Okay, we can get rid of all this physics stuff, and now let's create two reefs as children of this node. So we'll call the first one top reef, and that is of type reef, the one we just made. We're going to position it the x values of the children will match, will be in alignment with the reef system's x, so make that 0. And the y is the only thing that is going to change, whether it be up or down. So since the center point of the reef is in the very center of the reef, we want it to go up at least the width, at least half the width of the reef, plus half of the gap space. So we're going to go reef top. Okay, size, height. So that's how we get the height of the reef, and then we divide that by 2, and then plus whatever the gap space is divided by 2. That's because then we have to add the top reef as a child of the reef system. Okay, now copy all that because we're going to do something pretty much the same, but then call it bottom reef. Oops. Okay, and then copy bottom reef to where it said top reef here. Okay, so now this will be down that same distance, so, and then minus gap space. Okay, now in the game scene, we're going to go ahead and add just one reef system so we can see it and make sure it looks right. And let's do that here in did move to view. So after we add the jellyfish, we can say let rs for reef system, why not, equal reef system. And then we're going to pass in a gap space because we have to. And we can say 100. And then we add the reef system to the scene. And let's see if it appears correctly. We did not position the reef system, so it's going to appear to be around the origin. And here I positioned it to the point in the center of the screen. That's a snippet I use a lot, center. Okay. So here's a black box. Okay, very helpful. Things don't show up because Xcode doesn't like your pictures, so sometimes you have to just re-import them. That's okay. Here are my double reefs, and they are both children of a parent node, the center of which is right in here. Except we need to flip the top one around, and we will do that. We'll do that by going into our reef system class and giving top reef a y scale of -1. So that'll just flip it around. Alright, so we have our jellyfish and our reef correctly oriented. It looks like our gap space should be a little bigger. And you'll notice that he's not running into it at all. And its y position is going to be, oh, let's say around half the screen height. But we don't want it to be fixed at the same y or the same height the whole time. Or eventually we're going to want all the reefs to be at different y positions. Just like how the Flappy Bird pipes are at different height positions. So instead of just a fixed number here, we want to get a random number. So we're going to use a function that I made, and whenever I do that, I like to make a new file called helping functions. And you can be sure to spell it right, helping functions. Go ahead and import UIKit. And here's a code snippet I made called random CG float. So it gives you a number, a random number in between, or a range that you give it between the lower limit and the higher limit. So copy that down. Now back in our game scene, we will use that. So how about this? The Y position is going to be between 200 and 700. So let's make it move across the screen. So in did simulate physics, we are going to take, oh wait, we can't access. We have no access to our reef system because we declared it locally within the did move to view function. So we can't see it in the simulate physics. So should we make it global? Okay, we'll make it global for now. So in did simulate physics, we can say reef system. Oh, whoops. Okay, well, if we make it global, we have to change a couple things. We can't pass in gap space here because in the global scope declaration, it doesn't know what gap space is. Okay, so we could just put in something here, like 0, and then you can re-initialize it, rs, here. So that's one way of doing it. So we're re-initializing gap space here with gap space. Okay, now everything is safe, and we have access to rs down here. So here we're going to set its position every frame, and minus equals means, so that means every frame its position dot x is going to go down by 3. And let's see it move. Oh, right. If you reinitialize a variable, you have to declare it with a var keyword. You're mutating the variable. And there it goes. It was a little too low, but that's cool. Alright, let's close the app and reopen it. And there it is again. Whee! Now we're going to make reefs over and over again, continuously making them off to the right and then having them all slide across the screen and then disappear on the left. So that'll be our reef cycle. So we need some sort of function that's going to do all of this stuff. So creating a reef and then sending it across. And then we're going to call that function on a timer every time interval. So just for now, get rid of the update method and then make a new one. Let's call it create reef repeat. Let's just copy all this stuff with the reef system and put it down in our new create reef repeat function. Oh, and this will not be global anymore because we're going to keep on creating new ones. So let's declare it by saying let let's call it reef system, full name just to be very clear, and we'll say let, and then use that variable name throughout here. So we're going to create a timer within this create reef repeat function that's going to call itself. So for that we'll say timer. Here's my timer snippet I use a lot. Timer.schedule timer, and then with intervals, so we'll do this every 2.5 seconds. And we're going to say repeats is false because once we call the function again, this timer will be called again. And then we'll say self. This is a closure, so we need to say self dot create reef repeat. So if we call this create reef repeat, then it will start, it'll do the first one, and then it'll start the timer and then just keep going forever. So let's do that. We will have infinite reefs. So call it at the end of your did move to view, and we failed because, nope. Oh, right. Okay. Because we have to make them move. Inside did simulate physics, it doesn't know what RS is anymore. But we're going to have a bunch of reefs. So how do we get them all? So if you loop through all the children of the scene, you can say for child in children. So now within this loop, you can say child blah blah blah, and you can do stuff with the children. So all of these children are only SK nodes, but we only want the children that are of type reef system. So we're going to add some stuff in this for loop. So we say for case, and then we'll declare our local variable reef system. We'll call it reefs. And then we say as, and then the type, the class type, which is reef system in children. So now every time we say reefs, oh yeah, we have to say for case let reefs. Okay, now we can use reefs all willy-nilly. So reefs.position.x is going to decrement by 3. The way we have it, the reefs will get created and never get destroyed. They will go across the screen and keep going forever. There they go. You can see that our node count is increasing. 37, 40. And that will be very inefficient for our game. So now we want to get rid of them. So now, still within our loop, because we're looping through all the reefs every frame, we want to check for its position. So we want to check its X position if it's less than -200. And in that case, we will reefs.remove from parent. So that will get rid of the reef. So you can look at our node count now, and it's just going from 10 to 13 to 10 to 13, and we're handling all the nodes very well. So no memory is a leaking. I just want to tweak the gap space range a little bit. It was a little too low, so go ahead and change on line 80. So the reef system position.y will go from 400 to 400 from the top of the screen. And that's how you do that. Because remember, size.height represents the height of the screen, or the Y position at the top of the screen. Now to stop this timer, if we wanted to stop the reefs from being created, we couldn't do it like this as we have it now. That looks a lot more playable with our reef positioning. It's more in the center of the screen. Good. It's kind of creepy. So we have to contain this timer within a global variable. So we can go do that up here. So var, since it's going to be changing, and we'll say reef timer, and we're going to declare it as a type timer with empty initializers. Then when we make the timer here in create reef repeat, instead of just saying timer, we're going to assign it to our reef timer. So reef timer now equals the timer. This is a way of starting the timer, but then also assigning it to your global variable. Later on, if we want to stop it, the timer, we can say reef timer.invalidate, and that will stop that timer. We can do that anywhere in the program. Talk about making the jellyfish collide with the reef. Collisions, here we go. In order for any collisions to happen, we need to go up to our game scene declaration and have it inherit from this protocol called skPhysicsDelegate contact delegate. And then in did move to view, we have to say physicsworld.contactDelegate equals self. And now things can bump into each other. So with collisions above our game scene, what I like to always do is make a struct called bitmask. So in our jellyfish, remember one of the properties of PhysicsBody was category bitmask. This category bitmask is going to be assigned to a number, but it has to be a special number in the form of a power of 2. So it can be 2, 4, 6, 8. 2, 4, 8, 16, 32. So really what we could do is just assign this to 2. And anything that wants to collide with the jellyfish, let's say the reef. Okay, let's say the reef now, we're going to assign its category bitmask to be 4. So if we want the reef to collide with the jellyfish, we have to set the reef's collision bitmask to 2, because that is the collision bitmask of the number of the jellyfish. And contact test bitmask means that we're going to detect a contact and handle it in the game scene and do stuff with that. And vice versa in the jellyfish, if we want it to collide and do stuff with the reef, we have to set its collision bitmask and contact bitmask to that same number that the reef was with the category bitmask. Now that can get a little complicated, so to keep better track of that, we can substitute in this struct, and static just means that it can be seen by all classes. So anywhere in the program, if we say bitmask.player, it'll evaluate to this value. So this is just a notation saying that this is 2 to the power of 0, I believe. So we can say use these powers here to easily keep track of our bitmask numbers. Okay, so we can say player and reef. Those are going to be our 2 types of colliding bodies. Oh, and later on we'll do shark. Yes. Okay. So now our jellyfish, instead of just the number 2, we can say bitmask.player. And it's going to collide with bitmask.reef. And then, if we wanted to collide with more than one thing, more than one bitmask, you put a pipe there. So hit shift / to get the pipe symbol. And then, so it's kind of like a comma in a list. That's just the way you have to do it. Okay, use that same thing for our contact test mask. Okay. The reef. Okay, its category bitmask is bitmask.reef. It's going to collide with a player. It's going to detect collisions with player. And notice that it is not going to collide with shark. We want the shark to sail right through the reefs. Okay, our game scene's getting kind of big. So put the cursor anywhere and hit Shift, Option, Command, left arrow. Now we fold in all the codes, all of the functions so we can see them better. Okay, right here, under, right before did simulate physics, we're going to use one of the built-in functions called did begin contact. The reason we're able to use this is because up here we made game scene conform to SK Physics contact delegate. So now anytime anything collides with anything, this is called, and it's up to us to handle what happens. When things collide, inside of the did begin contact function, the only thing it knows is that two things collided, and we have body A and body B. So those are properties of contact, and you'll see contact has properties of body A and body B. It does not know which is which, so we have to sort that out for it. So we can make a new variable mask A, and that's going to be body A dot category bitmask. And then same with mask B. So now we can check if mask A and mask B match up to the two types we want to collide. So if mask A is bitmask.player and mask B is bitmask.reef, now we can handle the collisions. So anything we want to have happen when they collide can happen in here, right? Well, not quite, because body A is not always bitmask player, and body B, oops, let's make this a B, and body B is not always reef. Sometimes B is player and A is reef. So we have to put one big OR on this condition. So put this condition in parentheses and do a double pipe for OR. And now we can do the same condition, but now asking if B is the player and A is the reef. Now we can successfully do things in here. Okay, so let's print something. You hit me. Whoops. See why it wasn't working. So in did move to view where we said Jellyfish PhysicsBody, so we were reassigning the PhysicsBody and thus canceling out the PhysicsBody it had at first. So get rid of that, and now you will see the physics totally working. Okay, so, and it bumped into it. Nice. You hit me. Look at that. Nice. And I think just to tweak the controls on the jellyfish a little more, we're going to give it kind of an underwater feel, because right now it kind of feels like space. So we'll up the linear damping, so we'll have a lot of resistance to 2. And that's pretty much it. Let's just tweak the gap space a little more. Let's make it 350. See, he's kind of has more resistance and he's just floating through the water. Nice. Oh, one last thing. I think the reef speed should be global. Okay. We got jump speed, we got gap space. Let's do reef speed. Reef speed. That's going to be -3. Make sure it's a CG float. So now in did simulate physics, instead of just hard coding 3, we can say reef speed. Where'd my reefs go? Oh, because okay. Because we want a plus equals a value that is negative to make it go to the left. Should have said minus equals reef speed as +3. Alright, I like those nice wide gaps, and I lose. Okay, now let's be able to score a point. How do you suppose we can do that? In Flappy Bird, it's whenever you pass by some pipes. We need a global variable of integer called score. Now if you declare a number without any type, it'll just default to integer, or if it has a decimal, it'll default to a float. So there are default variables in Swift. Just know that this is of type int. Oh, and we need a best score to keep track of our best score. That'll start off as 0. Okay, now to tell if the player has passed by a reef. Now you could do a collision detection with some invisible bar, but I think that we can spare that and just do it here in did simulate physics, because we are checking this every frame. Let's make this more organized by putting in some comments. So remember, this is deleting. This first line is how we move the reef, and then here we're about to say how we score by passing by reefs. So this is, remember, inside this for loop, we're looping every frame through each reef that is a child of the scene. So if reefs.position.x is less than jellyfish's position, that means the reef has now passed the jellyfish and we can score a point. So what do you think is going to happen if we do this? Oh, and let's print the score so we can see what our score is. Whoopsies. So okay, look at that. Our score keeps printing and going up and up and up and up. Why is that happening? You guessed it. Because we're checking the reef's position every frame. And if it is to the left of the jellyfish every frame that it exists, this code will get executed. Alright, so we want another condition, maybe a property of the reef. Okay, go back to your reef system. We want to give it a boolean to tell whether or not it has passed the jellyfish. So we can call it has passed. Starts off as false. In the game scene, we can say, can put another condition on this, and if reefs has passed equals false, and that will be double equals since we're checking it, then we can set the reefs has passed property to true, and then score will increment by 1 only one time. 1, 2, 3. Hooray! Wow, we've almost got a solid game happening here. Okay, now we want the score label up here, remember that from a long time ago, to display our score. Now this is a very common skill having to do with dealing with your game scene. Okay, so the name of this is very important. So this is score label. So we're going to reference that in our game scene by making a global variable. Let's call it score label, easy enough, of type SK label node. And it's var because we're going to reinitialize it here. Score label is now equal to child node with name, and put in the name of the score label in the scene editor, and we cast it as a SK label node. That's because when it starts off in the scene editor, apparently it's only just a SK node. So since the score label is of type SK label node, it has a property called text, obviously, and it will say, in quotes, the way that you put in variables in the middle of strings, this is called string interpolation. You go backslash parentheses, and that's where you put in your variable score. So copy this line where we set the text to the score, put it down to where in did simulate physics where we actually score. So right after the score variable is incremented by 1, now we show it with our text. Alright, run it, see if it works, see if we score. Alright, and look at that, we're scoring! Now how do you suppose you keep the score in front of the reefs? Zposition. Because remember, every time something gets created, it gets shown on top of everything else that was created before it, unless the Z position is different. So we can set the score label Z position in code, or even better, we can do it in the scene editor here. Z position is 10.